Hi, everybody. Welcome to our presentation for the ECS 174 Computer Vision Final. We decided to re-implement the UNet paper, and we hope you enjoy.
Our project centers on improving UNet for biomedical cell segmentation. The first problem that we identified is that microscopy images are extremely challenging with cells overlapping and boundaries being weak. Our second problem is that the original 2015 UNet was trained with outdated methods such as no batch normalization, no ADAM, and trained on very small data sets. And our problem three is that UNet was mostly tested on small homogeneous data sets. But modern data sets like the Data Science Bowl 2018 are much more diverse, making generalizations harder. So the big question is, can we boost UNet's performance without changing the architecture significantly just by using modern training techniques and larger data sets?
So we used two data sets in this. We used the PHC, which was the original data set they used in the paper, and the DSB 2018 to see if the model could generalize. We also used data augmentation that they used in the model, in the paper, elastic deformation. We used two that we learned in class, random flips and crops, and normalization. And we used the original UNet architecture that was originally in Caffe and reproduced it in PyTorch with key initialization, which is key for ReLU, valid convolutions, copy and script connection, and pixel-wise boundary weighting, just like defined in the paper.
To modernize the UNet paper, we trained the training pipeline with several techniques that the original 2015 paper didn't use. We added batch normalization to stabilize gradients, switched to the ADAM optimizer for faster and smoother convergence, and introduced dropout to reduce overfitting. Also used the learning rate scheduler to adapt during plateaus and combined Dyson cross entropy loss to handle class imbalances and boundary accuracy.
In addition to that, we trained the UNet with the optimizers on the DSP 2018 dataset. And here is the prediction of the image compared to the merged instance mask and the predicted mask. So what is a merged instance mask? In this dataset, we had to merge all the instance masks so that it could generate a binary segmentation instead of the instance segmentation that it was meant to do.
So our results in the original paper, we used dice score because it's the most modern score, and IOU because it was well used in the paper. We got a 92% dice, and we got an 85% IOU. The training was very noisy because the batch size was 1, and the results align roughly closely with the expectations from the original paper.
Comparing that to the model with modern optimizers, you can see dice score improved to 96.2%. And it also had faster and smoother convergence, most importantly. And the IOU curves improved as well. On the DSP 2018 dataset, we only trained it for 50 epochs due to limited compute. And as you can see, IOU curves and dice score is just around like 51 to 66%, and which shows DSP dataset is pretty hard.
Our results showed three main forms of significance. We first demonstrated that the original UNet limitations were mostly due to outdated training practices, not the architecture itself. Modern techniques really helped us provide larger gains without changing the model significantly. Technically, these optimizations made training far more stable and improved boundary accuracy, raising our dice score from 92% to 96% on the PHC data set and smoother IOU curves. And finally, even though the Data Science Bowl 2018 was a challenging data set with many instance masks per image, our modernized UNet handled this complexity well. And this optimized training pipeline allowed the model to scale effectively and produce stronger segmentation results.
And when we evaluated the three models against each other, we found out that the DSB generalized well over both the data sets. But PHC, on the other hand, that the model we trained over PHC failed to generalize over the DSP dataset. We believe this is because of the complexity of the DSP and also the limited number of training dataset that the PHC had.
Thank you, guys.
Thank you.
Thank you.